Thank you, Chairman. So I'm Camille, and I'm working on fatigue crack propagation under an isothermal, multiaxial, and large-scale yielding condition. I am a PhD student between Safran and Ariane Group, and I am working under the direction of Vincent, MOUREL, Jacques, BESSON, and Pierre, ARNAUD. So a little bit of context. In turbo machines, some hotspots are locally submitted to severe out-phase thermomechanical loading, as you can see. So assessing and quantifying the impact of the thermomechanical loading on lifetime is needed. I am currently studying a combustion organ with a complex geometry submitted to a complex thermal field. Here, you have a zoom on the most critical area in the critical cycle for design. And as you can see, the loading is severe, as locally in the structure, von Mises stress exceeds the yield strength. And at the critical point, you have there the evolution of von Mises stress as a function of temperature. And as you can see, it is an out-phase anisothermal loading. And this loading also induces several plastic strain field with important plasticity, which is supported cycle by cycle with an amplitude of strain of 4%. To evaluate the impact of a crack in the structure, I manually insert a crack just there in the corner of the crack tips. And as you can see, the multiaxial loading is also severe, as the shear stress also exceeds the yield strength at the crack tips. So in the structure, when the temperature is low, the cracks opens, and then at high temperature, the cracks close and shears. So this also raises the question about the influence of contact and friction on crack propagation. So I study a combustion organ with a complex geometry made of asteroids by LPBF, and this part is subjective to a multiaxial thermomechanical fatigue that can lead to a potential crack. And so there is a real need to validate damage tolerance analysis. Asteroids is nickel-based superalloy, and LPBF is an additive manufacturing process. So that is why Ariane Group has developed an annealing heat treatment to relax stresses. And as you can see on the IBZ map, according a manufacturing direction, microstructure is well isotropic, structure heterogeneous, and there is no preferential crystallographic orientation. So it seems successful. So the aim of my study is based on experimental testing to identify a crack propagation growth model for specimen, and then to scale up and to study crack propagation for the components. So first, I'm going to present you the experimental fatigue growth characterization I've done. First, I conduced uniaxial isothermal loading fatigue test at 900 Kelvin with full cylinder shape specimen, one built horizontally and the other vertically. And the two specimens were subjected to the same loading, which is 1.2% of strain amplitude. And because of this intense loading, as you can see at the crack tips, there is a strain localization. So the crack is measured as illustrated here. And as you can see on the graph, fatigue cross growth is very high, and there is really no significant influence of specimen manufacturing orientation on crack propagation. So heat treatment is well done. Due to the loading of in the structure, I also conduce out-phase anisothermal loading between 400 and 900 Kelvin with hollow cylinders. So when the temperature rises up to 400 to 900 Kelvin, the mechanical strain decreases, and when the temperature decreases, the mechanical strain increases. So in this graph, you can really understand that it is an out-phase anisothermal loading. So just above the strain which is imposed on the specimen, you have the stress response, and you can see that just after a few cycles, because of strain hardening at 0% of mechanical strain, the stress becomes widely positive. And so at high temperature, the stress is negative, and then at low temperature, the stress becomes widely positive. So I measure crack length the same way as the other tests. And here the surface is rough because of manufacturing condition. And so I was able to compare anisothermal and isothermal loading influence for crack propagation. So you have in red tests at isothermal condition, and in black tests at anisothermal condition. So as you can see, crack initiation in anisothermal is earlier than in isothermal condition. And even if at 0.6% of strain amplitude, factoric phosphorus for TMF is much higher than for isothermal, when the amplitude tends to increase, when the amplitude increases, it tends to be the same propagation speed. So I also conduce multiaxial isothermal loading to study the impact of multiaxiality on crack length with a hollow cylinder. And here I choose to measure the crack length with a curvilinear measurement. So here you have a video of a mixed tensile and torsional test. Can you please launch the video? So as you can see, there is initiation of multiple microcracks, and there is really for each crack tips networks of microcracks, but only one preferential branching is growing, and you can also notice crack lips wears. So based on all this experimental result, I am going to present you the numerical model. So first, I set up a model at the specimen scale. I use a Chavoche type material with one kinematic and the one isotropic strain hardening and not on low. First, I implemented non-friction contacts, and here you have a zoom of an example of an experimental crack path insertion with Z cracks with a conformal remission technique. And because of the intense loading, numerical locking can occur. So here you have a finite element example model with a 1 millimeter crack insertion, which is subjected to monotone tensile text with an amplitude of 4%. And as you can see, with a quadratic element, the hydrostatic pressure have issues, have convergence issues. So that's why I use mixed reduced tetrahedral element to achieve good stress convergence under this condition and avoid any numerical locking. That are elements with one extra pressure degree of freedom at nodes. In this condition of high plasticity, the delta care approach is not relevant. So I use a non-local energetic model, which is based on the partition of plastic and elastic energy. These are, it is a non-local model because this energy are average in specific volume at the crack tips, as you can see on the images in red. And for this law, there are 5 parameters: lambda, G for plastic, and G for elastic, and M for elastic and plastic. And here, A is the crack length. So this type of law has already been validated for high plasticity and multiaxiality in the literature. So based on my experimental results, I have been able to try to determine a propagation law for a multiaxial test. So here in green, you have a pure tensile test, in black, pure torsional test, and in orange, mixed tensile and torsional test. You can see that it's relevant, but for the moment, it is not perfect. And I also try to do this for the experimental tests at 900 Kelvin. But because of the significant difference of loading, I don't obtain a reliable law. I try to take into account only the plastic energy, but it is not sufficient. So to conclude, structural calculation reveal multiaxial outphase thermomechanical loading with a significant shear and plasticity levels. The experimental testing demonstrates a strong influence of non-isothermal multiaxiality and strain amplitude on fatigue cross growth rates. And actually, the chosen model is able to model cracks and to take into account high strain level. But in the future, I am doing further tests to gain on the validation for the fatigue progress model, and also by taking account perfection in the model. Thank you.